Okay, let's run through a few properties of logarithms. Now, these are called properties of logs, but if you have a true understanding of what logarithms are, there's no need to necessarily memorize what we're about to talk about here. Think of them more like shortcuts. Okay. But again, if you're taking the approach that we have so far, where understanding that a logarithm is an exponent and the value of a logarithmic package like so is a singular number, and it's whatever number I raise this number to get this number, right? If you keep all of that in mind, then all of these properties are going to come pretty easily. They're just, like I said, they're more shortcuts than anything. So, for example, in this case, this logarithm represents a value that I raise a to get 1. So what power, ask yourself this question, okay, and I'll write it up here. A to the something power has to equal 1, right? What power is this, right? I kind of gave it away when I circled it, right? It's 0, because anything to the 0 power is 1. Now, what they're trying to express here as this property is that anytime 1 is the inside, let's call it the inside value of the logarithm, the output is automatically 0. Okay, and we saw that, if you want to get really crazy with it, we saw that as the x-intercept on the graph of a logarithm, right? Remember that a logarithm has an x-intercept at 1 comma 0, right? So if we put 1 into a logarithmic function, the output is 0. That's what we get here, right? That's why when you see that basic logarithmic growth function like so, that's why that intercept exists there. But long story short, when 1 is on the inside of the log, the output is 0. Okay? Here, what value do I raise a to get a? Right? So a raised to some power has to equal just a. Well, what is just a? A is a to the first power, right? We can always write anything as the itself raised to the first power. So what value is this? This is 1. So again, what's the shortcut here? When the base of a log and the number inside the log are the same number, automatically has a value of 1. Okay? How about this one? This one is kind of crazy, all right? And the best way to express it is this. What are logarithms, right? What have we said before? Logarithms are exponents, okay? If logarithms are exponents, and more specifically, they are exponents, okay? But logarithms are the inverse operation of a variable exponent. So think of it like this. Here's one way to interpret what this statement is saying. If we put a logarithm in the exponential level, right, then it's an inverse operation for the space that it's occupying. Okay, so it's almost like having an equation that says, x plus 4 minus 4, including the inverse operation in a space that undoes something that's already there. Okay, so long story short, if you ever create a logarithm, or if a logarithm with a base of a is an exponent for a, this operation undoes itself, and whatever is inside the logarithm is the value. Okay, so making a logarithm an exponent, okay, sort of negates this whole exponential process. And I know I'm speaking in ambiguity and some generalities, but it's a quick way to understand how this property works. And then we're just left with whatever's inside that logarithm. Okay, so for example, you're going to see 5 to the log base 5 of 3x. This is just equal to 3x. Okay, whatever's inside here. All right. This one, again, so common sense. It's so easy. Don't overcomplicate this. Okay, so what is this logarithm saying? This logarithm is saying if we raise a to some power, we get a to the n power, right? Whatever this is. What's the value of this? A raised to this power is equal to a to the n power. So what does this have to be, right? So simple, it might be confusing, but this is just n. Okay. And the way that we do this, okay, way that you'll see this happening is you'll get something like this, okay, coming up pretty soon. So what is this statement saying, right? With no base, we said this is a common log, so that's log base 10, all right? And with 1,000, 1,000 can be written as 10 cubed. So match the format here, right? If we have base A and then in here we have a power of that base, the value is just the exponent, okay? Because what power do I raise 10 to get 10 to the third power, right? 3. So the value of this logarithm is 3. So it's one way to use a property uh, to evaluate powers like so, right? But only if the base of the exponent matches, or excuse me, the base of the log matches the base of this exponent. Like that's not going to work for something like this, right? Because this is saying log base 3 of 16, and I don't know what power I raise 3 to get 16, right? So the bases here have to match in order for me to say it's just this number. Okay. Last but not least, we'll put this out here, but we're not going to use this for a while. Okay. And again, so common sense, so easy. It might seem complicated, but what we're saying here is that if you have two logarithms that are equal and they have the same base, the only way two logarithms can be equal of the same base is if the numbers that are inside those logarithms are equal. So we're going to eventually solve logarithmic equations, and we are going to end up with certain scenarios where we have a log on one side and a log on the other. And when that happens, as long as the bases are identical, we just drop the logs completely, okay? And we just have this statement, and it works both ways. So we're going to come back to this, and I'll reference it once we get there, once we start solving logarithmic equations, okay? So again, these are not necessarily properties that you need to memorize, okay? As long as you understand what a logarithmic expression is saying, okay? Which we've spent a great deal of time talking about.